Hydrogen storage plays a key role in an economy based on green hydrogen. In addition to physical storage of hydrogen, as a gas or a liquid, it can also be stored in or on other materials, or it can be stored chemically via chemical bonds. Chemical hydrogen storage in the form of gaseous or liquid energy carriers is the topic of this lesson. In particular, we will take a closer look at hydrogen's potential for utilization of CO2 and as a feedstock, for instance, for ammonia production. All this can be summarized under the term power to fuel. The respective fuels are generally referred to as e-fuels. In other words, green hydrogen can be used as a basis to obtain a variety of chemicals and synthetic fuels. In this context, it is important to know which are the most interesting synthetic fuels, how are they characterized, how are they produced, and what are the challenges encountered regarding chemical reaction engineering. We will illustrate all this using the synthesis of ammonia as an example. Among the most important synthetic fuels, which can be produced from green hydrogen and a carbon source, are methane, methanol, so-called Fischer-Tropsch synfuels, and dimethyl ether. As carbon source, CO2 can be used. It can be either taken from off-gas streams, or in future, CO2 could probably be directly captured from air. CO2 and hydrogen are then converted into synthesis gas, a mixture of mainly carbon monoxide and hydrogen, which is further catalytically converted into the respective fuels. A further potential non-carbon energy carrier is ammonia, which can be obtained from hydrogen and a nitrogen source, generally nitrogen separated from air. Let us now take ammonia as an example and have a closer look at it, its characteristics and its production. Ammonia, with the chemical formula NH3, is a, however, toxic, pungent-smelling, colorless gas that is highly soluble in water. It is the second most produced chemical in the world. Currently, ammonia is mainly used in the agricultural industry for the production of fertilizers. This makes up around 90% of its consumption. On an industrial scale, ammonia is produced using the famous Haber-Bosch process, a very energy-intensive process. The hydrogen storage capacity of ammonia is around 18% per weight. Ammonia has a high energy density in liquid form, which is about twice as high as that of liquid hydrogen. Compared to hydrogen, ammonia is easier to liquefy at atmospheric pressure. It is therefore easier to store and transport. Moreover, no CO2 emissions are generated during the combustion of ammonia. Green ammonia is therefore often seen as making a pioneering contribution to a decarbonized energy economy. As already mentioned, for large-scale ammonia production, a process known as Haber-Bosch process is used. This is an exciting process in terms of chemical reaction engineering, as we can learn a lot from it. On the one hand, this process consists of a large number of process steps before the actual conversion of hydrogen and nitrogen in the synthesis reactor takes place. At present, the hydrogen is still mainly obtained from steam reforming of methane. To start with, as part of the decarbonisation of ammonia production and to use ammonia synthesis for hydrogen storage, this part is to be replaced by the use of green hydrogen. On the other hand, we have to dig deep into the toolbox of chemical reaction engineering to achieve high yields of ammonia. This reaction impressively demonstrates the complex interplay of thermodynamics, reaction kinetics, skillful reactor design and catalyst selection. The synthesis of ammonia from hydrogen and nitrogen is characterized by a challenging chemical equilibrium. At elevated temperatures, the equilibrium lies far at the side of the starting materials. This results in a low final equilibrium conversion. Due to the exothermic behavior of the reaction equilibrium is shifted even further to the side of the starting materials as the reaction temperature increases. In the conventional Haber-Bosch process, sufficiently high conversions can only be achieved through a complex system of intermediate cooling and recirculation of the unreacted starting materials into the reactor. This already demonstrates the complexity and the associated technical challenges. In other words, a compromise has to be made when selecting the reaction conditions due to the thermodynamic characteristics and the reaction kinetics. Let us take a closer look at this. From a thermodynamic point of view, low reaction temperatures would be favorable in order to achieve a high yield of ammonia. However, if the temperature is too low, the reaction cannot take place even in the presence of a catalyst. Thus, higher reaction temperatures are required due to the reaction kinetics. In order to compensate for the unfavorable reaction equilibrium at higher temperatures, ammonia synthesis is carried out at higher pressures. In general, pressures of 250 to 350 bar and temperatures of 450 to 550 degrees Celsius are used. For this reason, intensive research is still being conducted into new technologies with the aim of intensifying and simplifying ammonia synthesis. Let us see where this journey will take us. We now conclude and summarize the most important points of this lesson. We have seen that hydrogen can be chemically stored through chemical conversion into a variety of energy carriers, including methane, methanol, Fischer-Tropsch synfuels, dimethyl ether, and ammonia. The energy carriers are characterized by a high energy density and high hydrogen storage capacity. However, every production process, even if well developed, has its challenges. We have discussed this in detail using the example of ammonia synthesis. It can be said that the production may be complex, and current research endeavors are still aimed at intensifying current processes and also at developing new ones.